Hello and welcome. This tutorial is based on the paper called Large-Scale Enrichment and Statistical Cyber Characterization of Network Traffic. We have many authors from different institutions. Of course, the paper has more details and I encourage you to look at that paper. This tutorial focuses on the implementations and steps towards working with large-scale data. Here's the outline for the tutorial. We begin with an introduction containing the motivation and challenges, the problem solved in the previous work, a look at the datasets and type of data, and an overview of the approach. Then we go into the approach and the results and summary. The motivation for this work rests on the amount of network data available for analysis. Modern network sensors continuously produce enormous quantities of raw data that are beyond the capacity of human analysts. Cross-correlation of network sensors further increases this challenge by enriching every network event with additional metadata. Additionally, we may need for that data to be anonymized yet still perform efficiently and quickly on large network datasets. We created an approach to cross-correlate large-scale data and tested the approach using billions of anonymized network data samples from the largest Internet observatory, CAIDA telescope, and tens of millions of anonymized records from the largest commercially available background enrichment capability, gray noise. Large volumes of enriched network data present opportunities to statistically characterize network traffic. In this example, we were able to answer the key question: what are the primary cyber characteristics of my network data? Such characteristics can aid in cyber defense by enabling focus on specific targets. To understand data with malicious intent and find trends to aid in cybersecurity defense, datasets from two data observatories, CAIDA telescope and gray noise honey farm, are analyzed and cross-correlated. The datasets contain network traffic found by collecting data packets from thousands of IP addresses that scan the Internet daily. The CAIDA telescope monitors the traffic into and out of an Internet dark space that is globally routed on a /8 network, carrying minimal legitimate traffic due to the few allocated addresses in the Internet prefix, making it a natural observatory for anomalous unsolicited traffic. Another sensor type is gray noise honey farm, consisting of thousands of servers that observe and interact with the Internet to analyze and tag the collected data. As shown in the sparse matrix, the difference between CAIDA and gray noise is that gray noise servers have the additional capability to converse with the IP sources to identify behavior, method, and intent. For this example, we're looking at a 30-minute window collected data on 4 different dates, 2 which are at midnight and 2 at noon. CAIDA collects exponentially more data over the same period gray noise does. Approximately 30 minutes of CAIDA data collection is equivalent to 30 days of gray noise data collection. Throughout the rest of the tutorial, we will use CAIDA start time due to the data being collected at either noon, represented by 12 and 4 ending zeros, at midnight by all ending zeros. Previous work have shown that 70% of the highest frequency sources in CAIDA are also seen in gray noise. Let us point out that there are 9 distinct values from the cross-correlated data of CAIDA and gray noise, which include actor, the participant sending packets over the network, spoofable, which is a binary variable that identifies whether the source IP has failed to complete a full connection, ASN, last seen timestamp as seen by gray noise, protocol port, which are the network ports associated with communication from the source IP, the operating system associated with the source IP. Source packet is the logarithmically bin number of packets sent from the source IP as seen by CAIDA. Classification of source IP by gray noise, this could be malicious, benign, or unknown. And CVE, common vulnerabilities and exposures. As for CAIDA, there is a source packet, which is not seen by gray noise. Here's the overview of the approach. Using D4 in Python, a dimension analysis is done with the help of tables showing parameters such as max value, the max count, and max fraction, followed by an analysis to explain typical records. Then we create a histogram to further analyze the variables through exploring trends and correlations, and finally present correlation findings to stakeholders. Our next item is the approach. The implementation design consisted of 3 parts, with additional steps. These 3 main parts serve as the outline to cross-correlate and analyze any large-scale data sets. First, we set up the data for analysis. This includes determining the variables to use for the analysis. These inputs in our case were the variables obtained from Kaida and gray noise previously mentioned. Second, perform a dimensional analysis to identify what variables to continue exploring. As shown in the diagram, we determined variables that did not need further exploring and variables that needed further analysis. Finally, with the use of D4M, we created graphical representations and probability distributions for better insight into the broader behavior of the network. Given the amount and type of data being handled, we use the Python library D4M. D4M is a breakthrough in computer programming that combines the advantages of 5 distinct processes to provide a database and computation system that addresses the problems associated with big data. Utilizing concepts of linear algebra and signal processing to databases through associative arrays while providing a schema capable of representing most data and low barrier to entry through a computing API implementation. Let me iterate that this library is the core tool that made possible to handle the amount of data. We encourage you to take a look at the Mathematics of Big Data book for more information and deeper understanding. The first step is to understand the type of data you're working with. In a Python notebook, we have imported the library packages used for this analysis. The libraries include D4M to work with a large amount of data. Depending on your type of data, you might also need to serialize and deserialize it using Pickle. Matploy was used to carry out the data visualization and graphs. NumPy was used to work with the arrays, and SciPy to work with sparse matrices. We also used other standard libraries, and depending on the type of data, you may require more or less libraries to work with. After the importation of the libraries, it is time to load the data. This is done by loading Pickle files into the dictionary with data and array name keys. The data we're using for this project are in anonymized TSV files. They are processed into D4M associative arrays. We deserialized or in Pickle the associative arrays to be used for example records. We then can go through each variable and find the most common values associated with those variables and how often they appear. We create tables to represent example records. The example record column will contain Kaida's collection start time, the variable of interest, the end row represents the source IPs associated with the variables, the end call represents the unique values per variable, n and z the number of non-zero values, max val is the most frequent appear value, while max count is the number of times the maximum value appears, and max fract, which is a fraction of the number of times the maximum value appears over each variable's total number. Depending on your type of data, there are many graphical forms of representation, and it is convenient to decide. In this case, the data for lasting timestamp was converted into a form that could be plotted. This specific example allows for the time to be plotted by day, week, hour, minute, and seconds. As we will see later in our output of this code, it made sense to plot the time by hour. A function for a general plot of value frequencies was created. This allows for most of the values to be plotted using a single function. Based on the values collected, there were two types of data, numerical and non-numerical. We had to work with both. Binning the data allowed for better organization and clarity. First, we needed to calculate counts of non-numerical data, bin those counts, then plot their frequencies. The numerical data in our case was already binned. All that was left to do was to plot the data. The next step was to use probability distributions for better insight. Previous work with this data shows that the heavy tail distribution are very common and emerge often. This probability distribution sheds insight into the broader behavior of the network. We can examine the distribution of value frequencies using robust selection criteria. Heavy tail statistical distributions verify time-independent statistical phenomena and illustrate general applicability of the Zipf-Mandelbrot model. This particular modified model allows the characterization of data with just two parameters. In the results section, we will be going over plots, tables, and exemplar records. The exemplar record reveals the characteristics of our network data. We found the max value and the max fraction, and based on those results, we determined the exemplar record. The actor, who is the participant sending the packets over the network, has a maximum value of unknown, appearing about 99% of the time across all 4 dates. CVE lists publicly known vulnerabilities in devices with related information. Records classified as benign or unknown do not have a CVE value, while each malicious records may have 0 or more CVEs associated with it. A single exploit is being used 90% of the time, that is CVE 2017-0144, referred to as Eternal Blue. Internet traffic communicates through packets. Those packets are classified as unknown, benign, and malicious by gray noise. It was found that 60% of the packets were classified as malicious. OS, or the operating system, comes from the source IP. 33 to 47% were found to be Windows 7, 8. Port protocol is a number that identifies the standard used to communicate with the computer's port. The most common, showing up about 22% of the time, was TCP 445, which corresponds to Microsoft networking. ASN is a number that identifies each autonomous system. It is a collection of connected Internet Protocol routing prefixes controlling the network operators. It is a varied ASN, with the most common ones appearing 5 to 10% of the time. The exemplar record then is that 99% of the time, an unknown actor running the Windows 7/8 operating system sends between 64 and 127 packets with malicious intent over TCP 445 with a non-specified ASN and targets CVE 2017-0144. The zip-Mandelbrot model exists in many of the Explore variables. Here we have the distribution of packets sent. We can see that for all 4 dates, they are very closely associated with each other. Our model closely fits all 4 dates. Using gradient descent methods, we were able to figure out what the parameters were for the model. The normalized plot shows that most source packets come from the low-traffic source IPs. Following closely with CIDA and gray noise source packets, the CIDA-only source packets show the same result: a high number of source IPs with low number of source packets. The protocol ports was plotted with the number of source IPs over the fraction of number of sources. We find that the normalized distribution demonstrates that many protocol ports were used by a few sources and few protocol ports were used by many sources, while the associated zip-Mandelbrot model still follows closely. Taking a look at the distribution of frequencies of ASN, we see that it is very linearly on a log scale, which is a heavy-tailed distribution. If we were to take a look at the ASNs, they are mostly used in telecommunications, including ISPs and wireless networks. For the lasting timestamp, we have the fraction sources versus the hours of the day. We can see how the last timestamp varied based on when it was collected. That is, the distribution is consistent across those with the same collection times. Midnight represented by red and orange, and noon represented by blue and green. The classification histogram gives us a better picture of the 3 types of classification. As we saw in the exemplar record, the majority of the packets were classified as malicious, while unknown followed very closely behind. This is an expected behavior, as we have gathered data from dark space containing mostly illegitimate traffic. This histogram shows the frequencies of the top 25 CVEs observed by CIDA and gray noise. This data, like all the other, was normalized. However, we arranged it on the descending form from top to bottom for clarity. The results show that the Eternal Blue CVE is the most common observed CVE. The histogram shows the top 16 operating systems observed by CIDA and gray noise. The most used operating system for attack launching is Windows 7, 8, with the unknown operating system following closely behind. This tutorial went over 3 main steps to analyze and cross-correlate large-scale data using Deform and Python. We used 2 large data sets, CIDA and gray noise, to demonstrate the methods. The main characteristics of our network data, traffic observed by cross-correlation, provides insight into the question, what are the primary cyber characteristics of my network data? The analysis revealed that certain adversarial activities dominate the traffic. The typical adversary is an unknown actor sending between 64 and 127 packets with malicious intent over protocol port TCP 455 using Windows 7.8 operating system and attempting to utilize CVE 2017-0144 or Eterna Blue. The modified Mandelbrot distribution models several different phenomena arising from the examined illegitimate traffic, including the packet distribution sent from source IPs, as well as the distribution of protocol ports and ASNs among source IPs. As a result of these models is that few source IPs send large numbers of packets, and that illegitimate traffic highly favors uncommon protocol ports and ASNs. Due to the previously mentioned, network traffic is caused by small types of cyber activities. Knowing these characteristics as a typical record enables focus on the main threats by statistical occurrences. As such, cyber defenders should prioritize protection from this adversarial behavior. We hope that you found this tutorial helpful. Please feel free to check out the paper for additional details. Thanks for watching.